Hi! In today's video I want to show you how to create a minimal and bootable Linux image. And I will test it on my phyBOARD session, which you can see here on my camera. I got the idea from this tutorial I found on the internet. Of course I will put the link into the description. In this tutorial, basically also a minimalistic Linux system will be built and will be tested on QEMU. But I will instead run it directly on my PHYTEC phyBOARD session, which you can see here. Okay, so what are the 4 parts you need to have a minimal and bootable Linux system? Well, basically you will need a bootloader, which will start Linux. You will need a Linux kernel image, a device tree to tell the kernel which hardware is connected to it, and you will need a root file system containing the libraries and applications you can run on your Linux system. So let's go over these 4 points one by one and let me show you how to get them. The first thing we need is a bootloader. Common bootloaders for embedded systems like my phyBOARD session are U-boot or Barebox. And I will go with Barebox here because Barebox is the default bootloader which PHYTEC is using for their boards and systems. So what does a bootloader do? Well, basically a bootloader initializes the needed hardware for loading Linux, and then it loads the Linux kernel, the device tree and the root file system into memory and starts them. Okay, so now we need to get a bootloader somewhere, and therefore I've connected to the FTP server from PHYTEC, because there I can find some pre-built images for what I need. And I won't build the bootloader from source, I will just take the bootloader from PHYTEC. So here you can see this barebox.bin file. This is a bootloader I want to use, so let me copy it and let me add it here in this PHYTEC folder where I will contain all the files and directories for today's tutorial. Okay, and after pasting the bootloader in here, we're done, so let's take a look at the next step. Okay, the next part is the Linux kernel and the device tree. And I put this together because when we are downloading our Linux kernel, it also comes with the device tree which we are going to use. So what I could do is I could open up my web browser and go to kernel.org and download the latest mainstream Linux kernel. But if you have a chip from a specific vendor or a board from a specific vendor, the chances are good this vendor has their own repository and a custom Linux kernel. Using this custom Linux kernel has some advantages. First, you will get an optimized kernel for the hardware you're using in best case, and the second thing is you will also get a device tree for your device, because normally in the standard Linux kernel a device tree for a specific board is not in here. Okay, so here you can see the Git repositories from PHYTEC. And down here you can see we have some different Linux repositories. And so this Linux IMX is the one I will use. The reason for this is on my phyBOARD session I have an IMX6UL chip from NXP, and so I think this is the correct kernel I should use for this. Okay, here I can see the releases, and you can see, yes, they are updated pretty recently, so this commit here is 3 days ago, so let's just grab it and use this for today's video. Okay, once is enough. While this is downloading, let's talk a little bit about the build environment I want to use. So here on my host machine I'm running Arch Linux, but for Arch there is no cross-compiler for Linux available for ARM architectures. But if you're using Debian-based distributions, you can normally find these ARM cross-compilers for Linux in the standard repositories. And I will use a Docker container as my development tool. So let's take a look at the Docker file. This is a really simple Docker file. Basically, I'm just importing the Ubuntu image and then I'm installing some packages. Here you can see the cross-compiler I'm using and some other programs I need to compile the Linux kernel and the root file system. Okay, so let me run the Docker. and I will mount my current folder as a shared volume inside my Docker container under opt source. And I called my Docker container arm-v7 builder. So let me start it, and now you can see I'm here on my Docker, and if I navigate into opt source, and well, as you can see the content here, so here we have our bootloader and the Docker folder, so we have access to it. Okay, the next thing I have to do is, after the download is done, I have to extract the Linux kernel into my working directory. So let me navigate to it again. This I have to do from my real host machine because my Docker container doesn't have access to the whole file system, just to this shared volume. And now I will unzip the Tor archive. Yes, let's go with this here and let's extract it here. And after doing so, I will have the Docker also available here, or the folder also available here in my Docker. This will take a little time. I will pause the video for a second and come back when the extracting is done. Okay, the extracting is done, so now we can build our Linux kernel. In this video I will only go very briefly about building it. I made a video about more details, and of course I will put the link into the description. So let me cd into my kernels folder, and here you can see the content. And a cool thing here is if I go to arm configs, you can see there is a config available for the chip I'm using. So here are multiple configurations for NXP's IMX chips, and I will go with this configuration here. And as I said, there is also a device tree available for my board. Oh, DTS. So if I search for a session here, you can see I have found multiple entries. So for example, this here is the device tree for my phyBOARD session, which I can directly use for the board. And in the normal mainline Linux kernel, I wouldn't have this device tree available in here. But now, as I'm using the custom kernel from PHYTEC, I have the device tree available. Okay, so now let's build the Linux kernel. The first thing I will do is I will have to create the kernel configuration. So my architecture is ARM, because the IMX6UL chip is an ARM-based chip. Then the cross compiler I will use is, I always forgot it, ARM Linux GNU. Yes, this string here. So let me copy this here. Okay, and the last thing is the configuration I want to apply, and this is this configuration here. So let's remove the tag here and let's build the configuration. Okay, the configuration is done. Now let's compile the Linux kernel. Okay, now the Linux kernel is compiling. This will take 10 to 20 minutes, and I will pause the video for now, and I will back when the Linux kernel is compiled. Okay, the kernel is compiled successfully, so now let's see what the compiled binaries are. First, let's take a look in arch, arm, boot. So here we have our compiled kernel image and a self-compressed version of the kernel image called set image. We will need this set image later for our SD card to boot up the phyBOARD session. And now let's take a look what's in the device tree folder. I will search for session again, but I will add .dtb. So here we have some compiled device tree binaries for the board, and this one is the one I will use for my board here. Okay, so with this step we have successfully compiled a Linux kernel image and our device tree, and now we can take a look at the next step. Okay, so after the kernel compilation is done, let's take a look at the last point, the root file system. So a root file system contains the applications and libraries which can be used on a Linux system. I will use busybox as a base for my root file system because busybox is very minimal, but it comes with a shell and the most important Linux commands you know from the terminal, like ls, cd, insmod, remove, and so on and so forth. Okay, so here I'm on the busybox webpage, busybox.net, so let me download the latest release of busybox. This won't take too much time because the binary is quite small, and then we will extract it. So, downloads busybox. Yes. Okay, and now we'll go back to my Docker container. You can see busybox in here, so let me cd into it. And now let's build it. Therefore, I will go back to the tutorial page here. So for compiling busybox, first we have to create a configuration. I will go with the default configuration. Okay, then let's do the compiling. And of course I will add, I will use all my 4 threads here. So now busybox is compiling. This will take a little while. I will pause the video for now and I will be back when busybox is compiled. So the compilation is done. After compiling it, you will install it. But this won't install busybox globally. It will just create this under install folder and will install busybox inside this folder. Okay, cool. So now I will create a new folder I will call rootfs, and then I will copy everything from busybox install into my new rootfs folder. Okay, the next thing I need is, here in my rootfs folder, I will create a new file I will call init. This init file is called by the Linux kernel after the Linux kernel is loaded successfully. And here I will just use this string here, or this text here. So what I'm doing here, I'm mounting my procfs into the folder /proc. I will mount sysfs into the folder sys, and I will create this dev mem device file, which corresponds to major number, device number 1, minor 1, I think. So this is what I'm doing here. And then I will print out Johannes minimal GNU Linux system. And I will also print out a warm welcome. Or yeah, just welcome. Okay. Now I will make it executable. Okay. Now the next step I will do is I will have to create some folders. So for example, currently if I look into my root file system, we don't have the proc or sys folder, but we want to mount something there, so therefore I have to add these folders there. So let's do this. Okay, now everything is created. The next thing I have to do is I will create a library folder in my rootfs, because you have to know I have compiled busybox with the shared glibc, and so I have to add the shared library for glibc into my rootfs. I can find these binaries under user arm linux gnu eap lib, and in here I have all the shared libraries I need. For example, here I have the libc.so, which is the shared library for the C library. So let me copy all the shared libraries here into my rootfs lib. Okay, and maybe let me check if glib or libc so .6. So here you can see the shared library is already compiled for ARM 32-bit, so this is the correct compiled library. Okay, and the last thing I will do is, while compiling the kernel, I've also created some loadable kernel modules, and I have to install these loadable kernel modules into my root file system. And I can do this with make arch arm cross compile is arm linux gnu eab and install modpath is our rootfs, and I want to do a modules install. Okay, so this will install all the kernel modules in my root file system, and I can find them under lib. Here I have this folder modules, which contains all the stuff I've all the modules from a Linux kernel. Okay, so the next step, or the last step we have to do to finish our root file system is we have to compress it, and we have to compress it and save it. And this will be done by this call here. So let's execute this. So basically this is finding everything in my current folder. It will add it to an archive, and it will use gzip to zip everything, and the result is a compressed archive containing our root file system. Okay, and after executing this command, here you can see our compressed root file system. So we're done with this step. Okay, so now we have all the parts together we need for our minimal Linux image. The next step is to create a bootable SD card image, which you can use for booting up our phyBOARD session. So let's start. First, let's take a look at the stack-up of the SD card image. You can see it here in this text file. So here we have the start of the SD card and the end of the SD card, and we need 3 parts on the SD card. So at the start we have a partition table telling the system which partitions are available on the SD card. The next thing we need is the Barebox binary. So this is the binary of our bootloader. And after that we have a FAT32 partition containing the Linux kernel image, the device tree, and the root file system. Okay, so here on my system I have connected an SD card and I have erased it. So here I have a SD card of 16 GB, and now let's partition it. Therefore I will use fdisk. I will create a new partition. It will be a primary partition. Partition number 1 is okay. Here the first sector the partitions should start would be right after the partition table. But as I need some space for the Barebox Bootloader, I will start the first partition at sector 8192, so I have space for my bootloader. The last sector is, I can go with the default. Now I have created a new partition from the type Linux, but I have to use the type FAT32, so I will type T and C, and this will turn the partition into a FAT32 partition. Okay, so this is the partition I'm going to create, and I will write changes with W to my SD card. Okay, cool, so now we have set up the partition table, but we have to create the partition. Therefore I will use mkfs.fat. This will create a new FAT32 partition on dev mmc block 0 partition 1, and I want to give it the label boot. So let's do this. And now you can see the new partition will be automatically mounted on my system under RAM media jroid boot. Okay, and the last thing I have to do is I have to write the bootloader to the SD card. Therefore here I'm on PHYTEC's documentation. I will use this command here. So what this command will do is it will take our Barebox binary and it will write it to our SD card. It will skip the first sectors where the table lies, and it will write it to the SD card. And our partition table won't be overwritten. So let's execute this. Done. Okay. And now the last thing we have to do is we have to copy the necessary files to the SD card. So first let me copy the root file system to run media jroid boot. And then I will copy the Linux image, which should be under Linux. Linux Arch ARM boot Z image, and I will copy it to my SD card. And last but not least, I have to copy my device tree overlay or my device tree file. 6UL PHYTEC. No. Where is it? Quite a lot. Yes, I think this should be it, and I will copy it also to my SD card. Now if I look what's inside the SD card, I have my kernel image, my root file system, and my device tree overlay. Okay, so I have prepared the SD card. Now let's try to test it. Okay, last but not least, let's do the testing. So I've already set up everything. I have plugged in the SD card, I have powered the board, and now I will connect over my serial terminal to my board. And let's hit the reset button here, so the system will perform a reset. Okay, you can see Barebox has started, and this is exactly the version I downloaded. And now to boot the system, I have to set some variables here in Barebox. I found out which variable I needed by hitting tab 2 times, and then I will get a list of available commands, but also of variables I can set. And basically I will need some of these global bootm variables. And under MMC, you can see my SD card is mounted, and here we have our 3 files: kernel image, device tree, and root file system. Okay, so now let's set the variables and boot the system up. The first variable points to our compressed Linux kernel image. So this can be found under mmc set image. The next variable is called global bootm off tree, and this points to the device tree which we want to use. And the last thing we have to specify here is the root file system we want to load, and this is mmc rootfs.cpio.gc. Okay, and to boot the system up, I will type bootm. Okay, so now it's loading our Linux kernel. It's loading our device tree, and then it will take a little time for the kernel to start, and it's also loaded the root file system here. So now it has to, now the kernel is starting. And after starting up, the kernel will execute /init, run init as init process, and now we get this print: Johannes minimal GNU Linux system, welcome. And the sh shell has started, so now we have a shell and we can access it. So the standard Linux commands are available here. For example, ls will list our current directory, or with uname -a I could print our current kernel, and this 5.10.72 is exactly the kernel I have downloaded from PHYTEC's webpage. What else can we do here on this system? So if I look into proc CPU info, here I have a file listing the CPU info. Or for example, I can take a look at the device numbers which are available on my system. So a lot of things are already working. Something else I could do, for example, let's toggle an onboard LED. This is cool. So I have the sys class GPIO export interface here. Class GPIO1 direction, and now I will set it to 1. GPIO value, and now you can see the LED here has turned on, and I can turn it off, of course, too. So this is already a usable GNU Linux system, but of course it comes with some limitations. For example, if I take a look into my device folder, you can see there are only 2 device files, but normally there should be a lot more, for example our GPIO chips, but they are currently not available because you need a device manager to create these device files. Normally you're using udev, but as I don't have udev installed, I won't have any device files here. Or listing the kernel modules is also not working because some informations are still missing here on my minimal build. But I think this is cool to see what you need to get a minimal GNU Linux system up and running on an embedded system. Okay, so I guess that's it for today. I hope you've enjoyed the video and learned something. In case you want to support my work, you can buy me a coffee on buymeacoffee.com/journals for Linux. So that's it for today. Thanks for watching and goodbye.